Okay. Very good morning, my dear students. In today's class, we will going to discuss two important concepts. One is called Principle of Superposition, and second one is the compound stresses, or what we call it as compound bars or composite bars, right? And if time permits, let me go or just touch upon the temperature stresses also in today's class, right? So quickly, in the last class, I think we discussed two important derivations. One is an expression for a deformation in a tapered bar having a circular cross section, and similarly, we have another one important derivation. One is a deformation in a tapered bar having a rectangular cross section, right? So I want you people to practice those derivation. Definitely, it is a mandatory. It's a compulsory. It's just a question which has been asked many times in your examination. So please try to practice the sketch and the steps, what it has been involved, and final equation, which will going to be for 5 to 6 marks in your examination, right? So as we discussed the stresses, the concept of strains or stresses and Poisson's ratio, and how to determine the deformation in a uniform bar or a stepped bar or a tapered bar. So one commonality what you have been noticed in all these analysis or on this discussion is the bar is being subjected for a load across their ends. Ends in the sense, if you take a stepped bar, if it is having 3 sections or 4 portions or 4 sections, whatever it might be, the load will be acting at the end. So in this, it is only across the end portions the loads are acting, and we have assumed that the same magnitude of load will be applied across the different portions of the bar. And based upon that, we have derived an expression for a deformation in a stepped bar. And we know how to calculate what is the deformation in such cases, right? So, but the same thing does not hold good in all the cases. In the sense, there may be a possibility that, or there may be some cases where the different portions of a bar will be subjected for a different magnitude of forces, and of course different nature of forces also. In the sense, not only the magnitude and the nature also. In the sense, the direction will be different from different directions. A different magnitude of forces will be acting across the different various sections. So in such cases, how to determine a deformation? So I think people are understanding what I'm talking here. So when I discussed a stepped bar, right? So in the stepped bar, so we have 3 different sections, and we have applied the load across the ends, So across the intermediate portions, there was no loads are acting. So the analysis was based upon each portion will be subjected for the same kind of load. That is, we have kept it as a P as the load across the each portion, and we have written the expression for the deformation in the each portion, and finally we have summed up, or we have added up all the individual deformations to get the overall deformation, right? So this is based upon assuming that each portion is subjected for the same kind of load. So this is not possible, may not be possible in all the cases, or may not be true in all the cases. So there may be some cases where we come across that different portions will be subjected for a different magnitude of stresses and different nature of stresses. In such cases, means what we generally term it as the bar subjected for a combination of loads, we call it as, or we can put it in the very short as a combined loading. Okay, so combined loading in the sense, each portion will be subjected for a different loads. So that is what we call it as a combination of loads, or combination of several loads, or a combined loading. In such cases, how to determine the stresses, or how to analyze the bars. This is the very important thing for being a mechanical engineer or being a design engineer. You should be in a position to know how to analyze such bars which are subjected for a combined loading. Okay, so for that, what is the analysis and what is the basic concept behind obtaining the stresses and strains and deformation at the end? So in such cases, so this is what the answer, what we will going to find it out from the concept, what we call it as principle of superposition, right? So we will discuss what is principle of superposition. We will going to have a statement of a principle of superposition, and we will take one simple stepped bar, or this is a bar with a different section subjected for a combination of loads, and how to draw the free body diagram of that, and how to get finally the stresses and the deformation. That is what we will going to discuss it in today's class in the first part. And later part we move on to the composite parts or a compound parts. Okay, I will give that introduction later part. Okay, so let us start. I think this slide is visible for everybody. The slide visible? Hello.
Yes, sir.
Yeah. So the principle of superposition. See, most of the machine members are subjected to the combination of various loads. So that is what I was talking in the beginning today. In the sense, when you look at the machine members, most of the machine members we can take it as, and they might be subjected for a combination of various loads. Combination in the sense it might be subjected for a tensile load or a compressive load. So it may of a different magnitude across different sections they might be subjected for. And the combined effect of load in the form of a stress and the strain may be found by using the principle of superposition. In the sense, so when the combination of loads are acting on a member or across a different section, so what will be the effect of this combined loading? So what we call it as a combined effect of the load. So this combined effect of the load can be determined in the form of a stress and a strain, and that by using a principle of superposition. Okay, so what is this principle of superposition states? Okay, so let us first take the statement of the principle of superposition, and later onwards we'll start understanding what is the statement means, right? So this principle of superposition states that total effect of several loads applied on a body is the sum of effects of individual loads applied separately. So please remember the statement. Statement is very important for the principle of superposition. It states that the total effect of several loads applied on a body is the sum of the effects of individual loads applied separately. In the means, it means that what is the total effect of several loads, so which will going to cause the deformation in a body. So let it be any type of load. The body is subjected for any kind of axial loads. The effect of the load is to deform a body. Am I right? So let it be either it is a tensile in nature or a compressive in nature. So the effect of these loads will be to deform. Either it will go into elongate, or it might go into it will go into contract, right? Depending upon the what type of load that body is or body is subjected for. So total effect of several loads, in the sense when you take the entire effect of the several loads which are applied on a body, is the sum of individual effects or effects of individual loads applied separately. So it is equal to the total effect of the several loads is equal to sum of the effects of individual loads. So when you apply the individual loads on the body, what will be the effect those individual loads will going to be produced on the each portion, that will be added together. It is a sum of the effects of individual loads applied separately. So this is what the statement of the principle of superposition. Okay, so now let us go into understand in a much more better way. So please remember, I will just explain, I will just state another one once this statement of a principle of superposition. Total effect of several loads applied on a body is the sum of the effects of individual loads applied separately. Okay, so now let us understand how we can explain this the statement of a principle of superposition. So to understand this statement of principle of superposition, so let us take a bar. Let's take this is a bar what I have shown here. So the bar, not necessarily it is a stepped bar, it is a bar. We are taking, it is made up of three different portions, 1, 2, and 3. 1, 2, and 3. This is a bar. It is not a stepped bar. It is a bar having three different portions or three different sections, which is represented as section 1, 2, and 3. And it has been subjected for the combination of loads. So look at here. So when I discussed a stepped bar, when you want to derive an expression for a deformation in a stepped bar, so what we have shown with respect to the bar is the bar is subjected for only the end loads. So P1 and P4 might be there in the analysis what we discussed previously. So only across their end of the bar the loads are applied, right? So now we are taking assuming the same magnitude of the load. Of course, there it is not a P1 and P4, it might be only P. So that's what I told you. They are equal in magnitude, but they are in opposite direction. They will going to constitute an tensile loading, right? So in this case, what we are observing here is, so look at here, the portion 1, across the portion 1, so there is a load P1 acting from right to the left, whereas across the another one portion of 1, there is a load P2 which is acting from left to right. Okay, so this is also applicable to the portion 2. So because it's a common side for the portion 1 and 2, so that P2 will be applied both to 1 and 2. Okay, similarly P3 and P4. When you look at this, this is constituting a bar having a different cross section subjected for a combined loading or a combination of loads. So in such cases, see that magnitudes are different. It is P1, P2, P3, P4. The magnitudes will be totally different. Their direction, the point of application of the load will be different. So everything is different, right? In such cases, whether we need to analyze or we need to consider the bar is subjected for a tensile load or whether it is subjected for a compressive load, that we don't know. So unless we know the values or the magnitudes of the P1, P2, P3, and P4 and making the static equilibrium condition or using static equilibrium condition, so we have to analyze the what is the net load acting on the each portion. Okay, net load, this is very important here. Net load acting on the each individual section 1, 2, 3, and then later we can easily calculate what is the stress induced. And once we get a stress, we can get a strain. Once we get a strain, we can easily get what is the deformation in the individual portion. And finally, we can get what is the total deformation in a bar. So this is how we generally approach such kind of problems to get the solution, right? So in the sense, what I mean to say here is whenever you come across such kind of situations, okay, so when a bar is subjected for a combination of several loads, okay, so now how we approach, how we get the solution for this solution in the sense, what is the total effect? So what is the deformation, whether it is the bar is getting stretched or whether the bar is getting contracted. So this is a very big question mark for us. So that how we can come to the solution. This is a very important thing, right? So to analyze such kind of bars, we need to analyze each portion separately. In the sense, we need to draw the free body diagram of the each portion. We need to indicate what are the forces acting on the each portion, and taking the equilibrium requirement, that is a static equilibrium requirement. So we need to calculate what is the net force acting on the individual portion. And then we can come to know whether it is a tensile in nature or compressive in nature once the magnitudes are known. Until the magnitudes are known, we cannot come to the conclusion whether it is tensile or compressive. So how do we know from the magnitude whether it is a positive sign or whether it is a negative sign? So if it is a positive, you will going to get, it will be considered as a tensile. And if it is a negative, we will going to get it as a compressive load. So here what I am just explaining over here is how we can draw the free body diagram and how we can use the equilibrium requirement and how we can determine the net load acting on the member. But we don't know whether it is a tensile in nature or compressive in nature. This can be obtained only once the magnitudes are known. That is, when we solve a problem, then you can come to know whether that individual portions are subjected for a tensile loading or a compressive loading. And based upon that, that will be subjected for either an elongation or a contraction. Right. So now what I have shown, I'm just explaining here is, I have taken a portion 1 over here. Look at here, the portion 1. That is just separately I have written. This is what we call it as a free body diagram over here. So this is an individual portion. What I will write here, I will just represent over here is, I will going to indicate what are the forces which are acting to the LHS and the RHS of the section 1. So LHS and the RHS. So this I will going to take it as an LHS, and this side we will going to take it as an RHS. As you are viewing, so towards your left will be the LHS portion, and towards your right it will be the RHS portion. So now I will going to indicate what are the forces which are acting across the LHS portion and the RHS portion of the section 1. Okay, so now this is the one what I have written here. It is the portion 1 here. I think you can see here portion 1, and towards the LHS or towards the left of portion 1, so there is only a one force which is a P1, which is acting from right to left. And towards the left, towards the right, so there are 3 forces which are acting, or 3 loads which are acting with a different magnitudes, P2, P3 and P4, and acting in different directions also. So what is the direction and what is the magnitude they are acting? The same thing I will going to indicate the loads or the forces to the RHS side of the portion 1. Am I right? So towards the RHS portion, there are 3 loads. We can see P2, which is acting from left to right, whereas P3, which is acting from right to left, and P4, which is acting from left to right. So they're in the same direction and the same magnitude I have indicated over here. I think you can understand this. Am I right? So if you have any clarification or if you find it any difficult to understand anywhere, you can stop me. Okay. So what I have writing here is just a free body diagram. I'm just taken the portion 1, and I'm just indicating what are the forces which are acting to the LHS, that is the left hand side, and what are the forces which are acting to the right hand side of the portion 1. So this is the indication of the forces or the loads which are acting on the either side of the portion 1, right? So now we will have a little sign convention over here, because sign conventions are very important when you are doing an analysis or analyzing any forces here. So for our convenient take, what we do is the forces which are acting. So please make a note of this. The forces which are acting left to right is positive. Okay, left to right is positive and right to left is negative. Left to right is positive and right to left is negative. This is what be the sign convention what we generally employ, and of course the same thing we're going to use it throughout our mechanics of materials, right? So I will repeat once again. The sign convention in the analysis here is left to right acting is the positive force, right to left will be the negative. Okay, so now Let us write down. See, in order to keep this portion 1 under equilibrium condition, okay, so the forces which are acting to the LHS should be equal to the forces which are acting to the RHS. So this is what we have used here. So here what's happening, the force which is acting to the LHS, it is P1, which is acting from right to left. That's why I have taken negative, minus P1. So this portion, this force should always balance with respect to the forces which are acting to the RHS portion, right? So therefore, minus P1 is equal to the forces which are acting to the RHS of section 1, which is P2. So P2 is acting from left to right, so I have taken it as a positive. Whereas P3, which is acting from right to left, I have taken it as a minus, that is minus P3. And P4, which is acting from right to left, I have taken it as a positive. So this is, so in order to keep the portion 1 under equilibrium condition, the net force acting on the LHS should be equal to the net force acting on the RHS. So this is what the equation we have written here. And if we know the magnitudes of P1, P2, P3 and P4, and if we substitute, and what will be the resulting value you will going to get it. So that will be the one which will go into determine whether the forces are tensile or compressive force. Okay, so when we solve a problem, we'll come to know whether the force is the net force acting on the section is tensile or compressive. Then you can easily understand, right? Is it clear, my dear students? If any have any clarification here, because this is a most important part of mechanics of materials. One of the most important concept in our mechanics of materials. Wherever you go, anywhere, any course, the concept of principle of superposition is very, 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 very important for. Any clarification anywhere? I think you can discuss before I just proceed for the next one. Yeah. Any doubts, my dear students?
No, sir.
Vasant, are you there?
Yes, sir.
Yeah. Any clarification, Vasant?
No, sir.
Naman? Naman Shivanand? Naman Shivanand, are you there? Mohsin?
Yes, sir.
Yeah. Did you understood any clarification, any doubts in this?
Yes, I understood.
Okay. Sayantan Banerjee?
Yes, sir, I understood. No doubts.
No doubt. Right. Just shall I continue?
Yes, sir. You can go ahead.
Yes.
Right. Thank you. Now, this is what I have just discussed with the one single portion, that is portion 1. Now, let us move on to the portion 2. Okay, same thing. So, how we have analyzed portion 1, in a similar way, we have portion 2 here. So, again, I will write the portion 2 separately, and I will going to indicate what are the forces or the loads which are acting on the LHS and the RHS side of the portion 2. Right. So, when you look at the portion 2 here, on the portion 2, so there are two forces acting, P1 and P2, and on the RHS side we have P3 and P4. Okay, so P1 is acting from right to left, whereas P2 is acting from left to right on the LHS side, and similarly on the RHS, so we have P3 acting from right to left, whereas P4 is acting left to right. The same procedure, no change, nothing. So in order to keep this portion 2 under equilibrium condition, the net forces which are acting to the LHS should be equal to the net forces which are acting to the RHS. The same concept will also use it here. So therefore, but when you are writing those summation or the net forces, so you have to apply the sign convention, right? So here, so minus P1, because it is acting from right to left, plus P2. So this will constitute the net force which is acting on the LHS side. And on the coming to the RHS, we have P3, it is minus P3 because it is acting right to left, plus P4, which is it is acting left to right. So this is the requirement for the equilibrium. For equilibrium requirement, we are writing the net force acting to the LHS should be equal to the net force acting on the RHS. So now from this we can easily calculate what is the net force with acting on the portion 2 or a section 2. Got it? So this is the analysis of portion 2. Moving on to the third portion. So when I take the section 3, so again I'm just representing the forces on the LHS and the RHS side. So towards the LHS of 3, we have P1, P2 and P3, and towards the RHS we have only one force, which is P4. Okay, so when you are writing for the equilibrium condition or equilibrium requirement, so using the sign convention, minus P1 plus P2 minus P3 is equal to P4. So the same sign convention will go to be holds good over here. So what we are conveying here, what I want to convey till now is, see, when you want to determine what is the total effect acting on, total effect due to the several load, that is the first line of the statement of a principle of superposition, the total effect of several loads. So when you want to calculate or when you want to determine the total effect of several loads, first we should know what is the net force or a net load acting on the individual portions. To determine the individual force or the net forces acting on the individual portions, so we'll go for, or we're going to write the free body diagram. So this is what I was doing till now. Okay, once you get a net load, this is very important. Please understand the word net load. Once you get the net load, and if you divide that net load by the corresponding cross-sectional area, got it? Once you determine the net load acting on the individual portion, and if you divide that net load by the corresponding cross-sectional area, so you will going to get the stress induced in that particular portion. Okay, net load divided by the cross-sectional area, you will going to get what is the stress induced in that particular portion, right? And once you get a stress, we can easily calculate what is a strain. So we know the relationship between a stress and a strain in the form of a Hooke's law. So sigma is equal to E into epsilon. Am I right? So E will remain constant if the material is same. If the material is different, E value will be different. So using that relationship, you can easily calculate what is strain. So sigma will be known from the calculation. E is the given value, and we can easily calculate what is the strain, that is epsilon. Once you get a strain, we can easily calculate what is the deformation. So strain is nothing but the ratio of deformation, that is change in length, to the original length. So original length of the individual portions will be known. So strain is calculated, and multiplying the strain with the original length, so you will going to get what is the deformation taking place in the particular portion. So that is, so each portion, if I want to know what is the deformation, that is in the portion 1, let us take it is a DL1, and in the portion 2 it is DL2, and in the portion 3 it is DL3. That is a deformation taking place in the individual portion 1, 2, 3 respectively. Right, this total effect, so this is the effect, that is net load. What is the effect of net load? Is to deform a portion 1. Similarly 2, 3, like that. So effect is deformation. So DL1 is the effect of the net load acting on the portion 1. DL2 is the effect of the net load acting on the portion 2, and DL3 is the effect produced due to a net load acting on the portion 3. So what is our statement of principle of superposition? States the total effect of several loads, that is the total change in the length, or total deformation in the length, or total deformation in a bar, is equal to sum of the effects of the individual loads applied separately, right? So the effects nothing but deformations. Please remember this, right? So therefore, DL, the total deformation, the total effect of the combination of load is the total deformation, which is equal to sum of the effects. That is the deformation in the portion 1, deformation in the portion 2, and the deformation in the portion 3. So this is the sum. So we are going to get DL is equal to DL1 plus DL2 plus DL3. So this is how we are going to explain the what we call it as this principle of superposition. Is it clear, my dear students? Any clarification over here? Is it clear?
Yes,
Anybody
sir.
can? Yeah? Okay. Right. I will just proceed to the next one now. Yeah, same thing only here. To find the force acting on the portion, calculate the algebraic sum of forces individually on its each side as shown in the figure above. That's what I was explaining. The forces acting on either side of the individual portion should be equal in magnitude and opposite in direction. So this is what we had discussed when if it is subjected for a tensile load. So what happens? The two forces acting on the either side should be equal in magnitude but opposite in direction. Then only we can say whether it is in tensile in nature or compressive in nature, right? Next comes, based on the principle of superposition, the equilibrium requirement, forces acting on each portion of the body are found and corresponding stresses are calculated. That's what I was explaining. So using the principle of superposition and equilibrium requirement, so we're going to calculate what is the forces acting on the each portion. And once you get the forces, then we can easily divide that forces by the corresponding area and corresponding cross-sectional area. Then we will going to get what is the stress induced in the each portion. Okay, stress induced in each portion is calculated as a ratio of corresponding load and a cross-sectional area. Net deformation DL in the stepped bar is the sum of the individual deformations in the each portion. Okay, that's what we have given in the previous mathematical equation. DL is equal to DL1 plus DL2 plus DL3 means it is the net deformation DL in this bar is equal to sum of the individual deformations in the each portion. So now coming to this, the last thing in principle of superposition is when we can apply this principle of superposition. So this principle is applied only when the effect of such effects such as stress and strain are directly proportional to the load which produce them, and strains produced are very small. So these are the two conditions under which this principle can be applied. In the sense, the stress and strain should bear a linear relation with the load, and the strains produced should be very small. Okay, so this is what we generally call the principle of superposition and the concept of principle of superposition. Any clarification, my dear students, in this regard before I just proceed to the next concept, what we call it as the compound loss? Any clarification with anybody? So you can have.
No, sir.
Yeah. Krutik, are you there? Krutik? Krutik N. Naman? Naman Shivanand. Shashank KS. Krutik can you speak? No? Can you unmute your microphone and
Sir,
can
present,
speak?
sir.
Krutik can?
No, sir, Shashank.
Okay, Shashank, you are there. Okay. Krutik?
Yes, sir. Sir.
Okay. Krutik? You're typing in the chat box. Okay. Samarth, are you there?
Yes, sir.
Did you understand what is the principle of superposition and the concept of principle of superposition?
Yes, sir.
Right. Any clarification, my dear students? Anybody?
No, sir.
You don't have any clarification? Okay. Thank you. If you don't have any clarification, I will proceed to the next concept. Okay. So, of course, the concept of principle of superposition, we will going to apply for some of the problems. I will going to explain the problems then you will going to understand how basically we just calculate the principle, how we can use the principle of superposition and how we can determine the net deformation taking place in the bar. Okay, right. Let us move on to the next one. What we call it as a compound bar or a composite bar. Yeah. So till now what we are discussing, a bar which is made out with a same material. Right. So of course we have made a stepped bar. A stepped bar, of course, I told you it may be made with a different material also. But a composite bar or a compound bar. So when we there are some examples or some cases where it is very much required for us to combine two different materials and use it for certain applications. When such different materials in the sense their properties will going to be different and their behavior with respect to the external loading will be different. So when such two different materials having different properties and behaving differently with respect to the external loads are rigidly fixed or fixed very hard or bonded together and apply an external load on that. So how these compound bars, how these bars or how these materials will going to be, right? This is what we will going to term it as a compound or a composite bar. A composite bar can be made of two bars of two different materials rigidly fixed together so that both the bars strain together under external load. In the sense, both bars are subjected for a deformation. Means they are strained. When you apply a load, when you apply an external load on the two different materials rigidly fixed together, so what we generally call it as a composite bar or a compound bar. And when you apply an external load on that composite bar, so definitely both the material or the bar will undergo a deformation. What we generally term it as both the bars will strain. As the strains in the two bars is same, so please remember here, the strains in the two bars is same, the stresses in the two bars will be different and depends on their respective modulus of elasticity. The amount of strain these bars will undergo will remain same. Okay, so when the strain remains same, the stresses will be different. Why? Because the modulus of elasticity of the respective material will be different. Okay, stresses are different and also depends upon their respective modulus of elasticity. In the sense, if the value of the modulus of elasticity is more, they undergo very less stress. So stiffer bar will share major part of the external load. This is very important. Please remember this. Stiffer bar in the sense the materials which are having more stiffness. So if you take a mild steel is more stiffer than the rubber. In the sense, the amount of load that is required for the mild steel to undergo a very small deformation is very more. It is very high compared to that of the amount of load required for the rubber to undergo that particular deformation. So that's why the steel is more stiffer than that of this rubber, right? So here in a composite bar, a stiffer bar will share major part of the external load. In a composite system, the two bars of different materials may act as suspenders to the third rigid bar subjected to the load. So this is another one important statement. In a composite system, two bars of different materials may act as suspenders. So if you have three different materials are there, two rigid material, two bars, and two bars are overhung, and the third bar will be subjected for loading. So these two material may act as a suspenders. Please remember this word, suspenders. Okay. In a composite system, the two bars of different materials may act as suspenders to a third rigid bar subjected to the loading, right? As the change in the length of both bars is same, different stresses are produced in the two bars. The lengths will be different, so therefore stresses produced will also be different. So this is a one simple composite bar I was just showing over here. So this is a simple bar. Let us consider a composite bar consisting of a solid bar of diameter small d and which is completely encased in a hollow tube of diameter d. Hollow tube of diameter d and inner diameter capital D subjected to a tensile force P as shown in the figure. So we have a solid bar, okay, and solid bar is completely enclosed in a hollow tube. So the diameter of the solid bar is small d, whereas the outer diameter of the hollow tube is capital D and the inner diameter is small d, and it has been subjected for a tensile force as shown in the figure. Okay, so this is an example for a composite bar. A solid bar enclosed within a hollow tube, and it has been rigidly fixed at their end, and it has been subjected for a tensile load across their ends. This is a typical example for a composite bar. So solid bar made with a different material, hollow bar will be made with a different materials, right? So now let the extension of the compound bar be L and be L delta L, and ES and H be the modulus of elasticity of the solid bar and a hollow bar tubes respectively. So here one important thing you have to remember. So solid bar made with a different material, hollow bar is made with a hollow tube is made with a different material. So therefore they will have the different values of modulus of elasticity. E suffix S corresponds to the modulus of elasticity of a solid bar, whereas E suffix H corresponds to the modulus of elasticity of the hollow tube. Okay. Let sigma S and sigma H be the stresses developed in the solid bar and hollow tubes respectively. The change in length of the solid bar is equal to the change in length of the hollow tube. As we can establish the relationship between the stresses in the solid bar and the hollow tube. So this sigma S into L divided by E of S. So how we have got this expression means it is just a PL by AE. PL by AE, the expression you know. So P by A we have written in the form of a sigma. Okay, please don't get confused with this expression here. Sigma S into L divided by E of S is equal to sigma H into L divided by E of H. So this is the deformation taking place in the change in length of the solid bar is equal to the change in length of the hollow tube. So this is a deformation in a solid bar and this is a deformation in the hollow tube. Is it clear? Okay, so this is the expression derived from PL by AE. P by A, I am taken the term P by A as sigma here. Is it clear? So now we will going to write sigma S. So just rearranging the terms, LL will get cancelled. Sigma S is equal to sigma H into ES by EH. ES by EH. So now the ratio of the modulus of elasticities of the two different materials. See, this ratio is there, no? E of S, E is S by EH. E of S by E of H. This is the ratio of modulus of elasticity of the two different materials because it is a solid bar and this is a hollow tube. This ratio, we call it as modular ratio. See here, ES by EH is called the modular ratio. Please remember this. This is very important from competitive examination point of view, and wherever you go, this is I've been observed many times. This modular ratio has been given. See, modular ratio is the ratio between the modulus of elasticity of the one material to the modulus of elasticity of the other material. Or we can say it is a ratio of the modulus of elasticities of the two different materials. We call that as the modular ratio. This is very, very, very important. So please make a note of this. Okay. So I think it's time now. I will just stop at this point in today's. Let me continue these things in tomorrow's class, means day after tomorrow's class. And So can you, we all request you to switch over to the quiz. So Google Classroom, I will just going to assign the quiz over there, and please submit your quiz there. Okay. I will just continue with these things in the next class also. Okay, don't worry. I want everybody to just switch over to the Google Classroom immediately. Yeah. So quiz is assigned there. So you can take up the quiz. Please submit within 11:50. Only 4 questions are there. I want everybody to submit that. So fill in the blanks is given, you just type the answer. So in question number 4, there are 2 words to be typed here. 2 different words are there. So you have to type both the words over there. Yeah.
So can you share today's lecture video in Google Classroom?
Yeah, definitely I'll put. All other lectures have been just
Sir,
posted.
yes, the
Hello.
first module PPT can you share, sir? Yes.
Yeah, once I just complete the module, I will just put everything. But videos will be
Sir,
there.
today I missed to note few points. So.
Sorry?
Sir, I missed today to note few points in compound bar. So can you show that slide once?
Yeah. Just take the quiz. I will just show that. It will be there in the video. You can see that video. You can watch.
Okay, sir.
Uh,
Sir, I submitted the answer. May I leave?
yeah. You can. Once you submit, you can take. No problem.
Thank you, sir.